Yes, Professor, we request you to please deliver your talk. Thank you so very much.
Okay, so should I start?
Yes, sir.
Okay. So welcome everyone. Good afternoon. So today, this is the very first lecture in machine learning. And I'll cover very basic things in this topic. So mostly I'll be covering regression and classification as two major topics. So here is the outline of my today's lecture. First, I'll just briefly introduce what is learning or machine learning and some exciting applications, and then different types of machine learning. And then the main topic of this lecture. So I'll cover one type of learning, which is called supervised learning. So I'll come to the details of the definition of this learning. So where I'll cover two major techniques, regression and classification. So what is machine learning? I think every one of us know. So there are many definitions. So simply I can say it automating the automation. Or
yeah, Professor, sorry to disturb you. Can you make it full screen in your presentation?
The presentation slides?
Yeah, full screen, yeah.
I think then I may need to change the platform. So it is not full screen, right?
Yeah, your slides are visible actually from on the left side, other slides. So I thought.
Okay. Okay. Then maybe it's better to switch because I have just switched to iPad because I need to write these things.
No problem. So then you can, no problem. You keep it like this, yeah.
Yeah, I think I just switched from PowerPoint to here so that I can just write on my screen.
No problem.
So that's the main
problem.
thing. So in markup, yeah, okay. So getting computers programmed to program themselves. So basically, what is automation? Automation is just writing some software codes to do some task automatically. So here the main bottleneck is that writing the software. Sometimes it is very complex to write a software code to do the automation. So rather than that, what we can do just write automatic programming. We'll give the data and computer writes the program itself to do the task. So this is in a nutshell machine learning. So I think we can see a block diagram to make it clear. So in traditional programming, what is the input? The input is data and program. So for example, if you have an array of numbers, a list of numbers, and you want to sort it, then you need to write a program, sorting program, to make it a sorted array. So here the input is data and your program code that can sort the data. And what is machine learning? So here we don't have program. We will not give the program as input. So we will give data as input and the desired output. Here the data is unsorted array and output is sorted array. From the input and the output, the machine learning task will write a program, generate a program that can map from input data to the output. I think here the main difference, here machine learning programs generate a function or generate a program that can convert input data to the output data. So this is the basic difference of programming and machine learning. So in programming, we need to write some codes to convert data to the desired output. In machine learning, we have an output, we have an input and desired output, And we have to find a function that can map from input to the output. Okay. So there are many applications. I think we know all about these things, like Chat GPT is in exciting machine learning applications, web search, autonomous driving, computational biology. You can just name your favorite area. There are applications there for machine learning. So formally, so if we want to define machine learning formally, how can we define? Basically, this is a program that learns from experience. E, with respect to task T, the experience here is data, task T, your goal, and performance measure is P. So if the performance of this program improves with the experience, I mean, the improves with more data, then we call it learning. So here are three parameters. One is experience, that is data, and we have a goal, which is T, and we'll have a performance measure, whether we have achieved the task or not. So based on this, we can call it a learning. If with more data, we can learn better. Okay. So this is a simple example, like play checkers. So if the task is play checkers or play chess, just a computer game. So, and the performance, we can measure the number of times a computer program on the game. It can be checkers or it can be chess. And the experience would be the number of times the computer plays the game with itself. So we can just formulate like this, any problem, like any machine learning problem. What is our goal? What is our data? And what is our performance measure? So if we can see that we as more as we play, we are improving our performance, then we can say that the computer program is learning something. Okay. So you can basically stop me anywhere. So I'll give some pause after these basic things, and in transition of every subtopic. So I'll give a break for question answer. So in machine learning, so there are like thousands of machine learning algorithms you can see every day, and hundreds new in every year. I think now nowadays it's hundreds new in every month. And every machine learning algorithm, the current or past or future, they have three main components. One is representation, another is evaluation, and another is optimization. These three basic components. So what is representation? Representation is like different types of learning. So I think many of you may know, so I am assuming you don't know. So there are many different class of applications. I think definitely you have heard deep learning or neural networks. This is one type. Today's lecture, we will see linear regression. This is another type of learning. So this is the different representation of learning, like what you will learn. So in some algorithm, you will learn many parameters. In some algorithm, you will learn few parameters. In some algorithms, you will learn some rules. And in decision tree, you will just build a tree based on your data. So there are many things. And today also we'll see some example of support vector machines. So there are many representation of your learning algorithm. You have to choose one. So whether you will choose neural networks or linear regression or decision tree or support vector machine, it will depend upon your task, what you need to do. And also it will depend upon how much data do you have. So you cannot basically choose deep learning or deep neural network if you have small amount of data. So I think you will learn these things as you go by this course. So then what is evaluation? Evaluation is just you have to have a measure whether the machine is learning something or not. For example, in here, so you can measure it as an accuracy or precision or recall or squared error. I think these things, we can omit these things because you'll just go through these things again, or likelihood or posterior probability. So these things you can use as evaluation, but it again depends upon your applications or the problem that you are solving. Then the third, this is more like technical things. This is optimization. Maybe current days, you don't need to worry about the optimization that much, but you need to know these basic things. So the optimization, when you try to find solution, basically you have to have some optimization algorithm. So today, luckily, we'll see two optimization. One is gradient descent and another is linear programming. And there are other kind of optimization also, which we call pre-research. So how to find the optimum solution? Maybe in machine learning, you will start with some very rough solution, and then you will just iterate over time and then find a good solution. So how to iterate over other solution space, in the solution space. So this is actually called optimization. Okay. And lastly, there are many different types of learning. So we can broadly categorize into three different types of learning. One is supervised, another is unsupervised, another is reinforcement learning. So what is supervised learning? Supervised learning, here you have leveled observations. Leveled observation means you know the contour. For example, if you have input, for example, if you want to classify an email, so email can be spam or non-spam. So the email is xi, you can say this is the input, output is 1. If it is spam, output is 0 if it is not spam. So if you have some level data, you have real world observations, and you have some ground truth, then we can learn from there easily. So you have some ground truth available, then you can train your machine. And when it comes to inference, like when a new data comes with no level, then you can generate a level. So this is called supervised learning. So you have leveled observations. In supervised learning, there are, I will come to the details of these two techniques. There are two main categories. One is classification, another is regression. So very briefly, the classification problem is you have to decide which class the input belongs to. For example, it is like if you want to classify your email, whether it is spam or not spam, this is a classification problem. And in regression, this is continuous like target. So if you want to predict the temperature, like tomorrow's temperature, then this is a regression, because it can be 22, 23, you cannot just basically classify. So this is a continuous value that you need to predict. And the unsupervised learning, this is not our topic today, but here the main difference is this is unlabeled observation. Unlabeled observation means you have lots of data, there is no label. For example, you have lots of news items. I don't know which category one news items fall into. So for the news item, if you have lots of news item and you want to find different categories of news item, you can do clustering. Clustering means just grouping news item based on category, like sports, politics, or entertainment. So you can categorize based on the content. So there is no labeled observations there. So you can just download news without any label. Then you can do the clustering. This is called unsupervised learning. And another one is very popular nowadays. So the chat GPT also relies on these enforcement learning. So this is basically reward from sequence of actions. What is that? For example, if you want to train a dog, so when a dog does some good thing, you give her a biscuit. Or when he does some bad thing, you are just not giving anything. So this way, you can train your dog how to do good things. For a certain actions, you can reward, and for certain action, you can penalize. So this is called reinforcement learning. So the ChatGPT, the performance of the ChatGPT also improves a lot because of this kind of reinforcement learning. There are lots of crowds, there are lots of like crowdsourcing people who did this kind of thing. When ChatGPT gives you an answer, you can just rate it, whether this is good, this is a perfect answer, or there is something wrong in the answer. Then the learning algorithm can learn itself. Okay. So any question after this, like the different types of learning, like supervised, unsupervised, and reinforcement? Okay. I think then I'll move to the next part of the lecture, which is called supervised learning. So this is the main topic. So as I said, in supervised learning, our task, so we have some level data. From the level data, we want to develop some algorithms so that it can level some unseen data. Here is a toy example. So if you see here, this is a chart. This you can say X. So the living area of a house. And here, this is the price of the house. Like if the living area is 2,104, the price is 400K. If the living area is 1,600, the price is 330K. So there are lots of pairs. This is X1, this is Y1, this is X2, this is Y2. So there are lots of level data here. We can see the plots. This is X, this is Y, right? So from this data, so you have some level data. So from this data, can we predict the price of a house given its living area? So this is the problem. Now, this is very simple problem, but this is, you can say, that supervised, the definition, like the problem formulation of the supervised setting. Okay. So what is the goal? I think this slide is important here. Here you have given a training set. We have seen in the last slide, the training set is X, Y pair. X is the input, Y is the output. The input can be very long, not only this living area, it can be like area of the house, or it can be the location of the house. There are many things it can incorporate, the X. And the output is Y. What is the price? So what is our goal? We should basically learn a hypothesis, or we can find a hypothesis. Hypothesis is a function, just a function. So we have to find a function that can map X to Y. So if we see this block diagram here, so this is the like block diagrams of a supervised learning settings. This is your training set. This is your learning algorithm. This is your hypothesis space. What is the hypothesis space? You have to find a hypothesis. Basically, from a large hypothesis set, you have to find a hypothesis. So hypothesis can be different for different kind of learning algorithm. Okay. So we'll see the different types of hypotheses. So here there is some assumption. When you design a learning algorithm, you have to assume what is your hypothesis set. And from this hypothesis set, based on this training, so in this hypothesis set, there can be many hypotheses, H1, H2, H3, there are many hypotheses. That means there are many mappings of X to Y. So you have to find a particular hypothesis that best fit your training data. And then when you give X as an input, this is unknown data. This is not training data. This is unknown data. So that using this function, you can predict the value of Y. this is the block diagram of all supervised learning. So you have to choose a hypothesis set, and you have to choose a learning algorithm, and you have to have big training examples. And the first goal is to learn a function, h. Then the learning is done. Then this part is not learning. This is just evaluating your query or inference. So after learning, you got an h, and then you can give x as input, and using this learning function, it can predict a value y. So this is the supervised learning. So supervised learning, it can be of two types. Basically, one is regression, another is classification. As I said, when the target variable is continuous, for example, predicting the temperature or predicting, for example, humidity, so or predicting the house price. So these are like predicting a continuous value. So then we call this as regression problem. Okay. Then what is classification? When the target variable takes only a finite number of discrete values, for example, spam, non-spam, spam, non-spam. This is a binary classification, right? Or you can identify digits, 1, 2, all up to 9 digits. So these are called classification. From handwritten character, you can identify digits. This is also classification problem. So first, we'll go through the regression problem. How we can do the regression. I think many of you know, but I am assuming no one knows anything about machine learning or basic like statistical regression kind of things. As this is the introductory lecture, I am covering like very slowly these topics. Okay, this is again the house price example. So here, this is the living area, x-axis, and house price is y-axis. So this is our level data. Now, we have a query, like what will be the price for the living area of 220? Here, 220. So how can I give the answer from this known data set? So basically, what we can do, if we can represent the training data, here, these are the training data cross. If we can represent this training data using a representative line, because we can see this is some kind of linear relationship. So if we can represent this training data using a line, then it is easier. We can predict any unknown value. For example, what is this line? This is basically like in primary school math, you know this equation, right? Y equal to mx plus c. This is a straight line. Or y equal to ax plus b, what same thing. So this is a straight line. So if you know the value of the one variable, then it is easy to predict y, right? So because getting a line, you have to know a and b, or m or c. This is the same thing. And when you give x as input to this line, it can give you y, right? So just you can replace x and a and b, then you can get desired y. Here, y equal to 200k, okay? So this is the simple linear regression problem. So now there can be many lines, right? So here we have seen just one line. So there can be many lines. For example, here in this figure, you can see one line is purple and one other line is green. So both can represent these points, right? But which one is better? So which one best fits the example. So this is our problem. So here the straight line. So I have told you the hypothesis set in my, for example, in my architecture slide. Here, this is the hypothesis set. For the linear regression, if we go here, so what is the hypothesis set here? So here the hypothesis set is all possible lines. So H basically can contain any line. It can be this line, it can be this line, it can be this line. I restrict the hypothesis set using two parameters, theta 0, theta 1. Theta 1, you can say this is B, and you can say this is A. Okay. So we have just two parameters. That's why we have restricted our hypothesis space as straight lines. So from this hypothesis space, I mean number of straight lines, candidate straight lines, I need to select one particular straight line that gives you the best result. Okay. So I have used many terms, so it will be clear, like in the subsequent slides. Okay, next. So here you can see that I'm assuming the hypothesis is straight line. That's why I can have this kind of line. So there can be other hypothesis space too. For example, if you have just a single variable, right? X, living area. So you can just assume that the hypothesis is this one. What is this? It is independent of X. This is just axis aligned line. This can be a hypothesis. And using this axis aligned line, you can basically try to best fit the training examples. The second one is, this is straight line. This is another hypothesis space. Here, this is the intercept, and this is coefficient of X. So this is straight line. And you can have higher order hypothesis. For example, here I use only one order, X. We can also use another feature, which is the square of this living area, to have high order polynomial. This is high order polynomial, right? This is another hypothesis set. So if you choose this, the hypothesis set will be different. If you choose this, hypothesis set will be different. If you choose this, hypothesis set will be different. But currently, we are assuming that we are considering this straight line as our hypothesis set. Okay. So any questions so far? Okay. So we are considering here this as our hypothesis set. So this is a straight line. And X is the input feature vector. Input feature vector means there can be many features. This is a particular example, X. And it can be, the features can be X1, X2, X3, ... So this can be the living area. This can be the number of bedrooms. Okay. This can be location. So the input can have many features. This is the features. And using this feature, we can have a hypothesis. So this is the linear combination of feature space, right? Theta 0 plus theta 1 x1 plus, because X dimension here, we are assuming that the dimension of X is n. For every input, you have n features. Living area, number of bedrooms, location, like the area of your land. So these are the features. So for each example, so we are assuming there are n features. So then our function should be, this function should be the linear combination of these features. So this is the linear combination of this feature. And we have another term here, theta 0. This is basically the base or intercept or bias. So here we add theta 0. We need to add bias here. Just to make it a general formula, we are adding here x0, where x0 equals to 1. This is not a feature. This is just a constant. Okay, so these are the feature, x1, x2, xn, and this is the just a constant, x0, to make it a like good formula, right? So this is now hx. What is hx? This is the linear combinations of features. We don't know theta. This is just a number. Theta 1 multiplied by x1, theta 2 multiplied by x2, plus theta n multiplied by xn. So these are just the linear combination of these features, and we have this hypothesis. So we can write it like this, right? hx summation of I equal to 0 to n theta I xi. Okay, this is for a particular example, for a particular input. And I think you know the linear algebra, right? So you can write in a vector form. This is theta transpose x. Because when you want to multiply this, one have to be column vector, another should be row vector. This is theta 0, theta 1, theta 2, theta n, and this should be x0, x1, xn. So when you multiply this, you can write it like this. Okay. So then now the task is to find the best hypothesis. As I said, the best hypothesis, the best line from all possible hypotheses. So we can assume here the best is the one which gives smallest error on the training data. Then the cost function. What is the cost function? Basically the smallest error of all the examples. For example, you have m examples. So if I just draw it here, 1, 2, 3, m examples. This is one data point. This is another data point. And you have feature 1, 2, n features for every data point. So this is x3, x3, 1, x3, 2, xn, x3, n. This is one example, the third example, okay? And you have m examples here. So you have to find the error of all the examples of the training data. So what is the error? Here we are using least square. So this is the prediction of your model, like predicted value. And this is your ground truth value, right? Ground truth. This is predicted, this is ground truth. So ground truth is here, like in the data set, you have the ground truth, right? Y1, Y2, Y3, Y4. So for each data, you have the house price. This is the level data. And using your model, for example, whatever we want to find, this hypothesis H, you are predicting a value. This is not necessarily equals to this one. For example, you have ground truth house price 200, your predictor predicts is 180. Then what will be the error? Here the least square error, 200 minus 180 square. So you have to add all the errors from 1 to m. I'm just taking a break. because I think otherwise there will be noise.
Neha, please pause it for a while.
Yeah, we can start now. Okay. Sorry. Yeah, so there is one question in our chat box. So what is ground truth? Ground truth means the level data that you have. For example, you have some house price data already in your hand. So there are some previous examples you have. So this is the living area and this is the price of the house. So this is the ground truth. This is the real world data that you have collected from past. Okay. So this is the ground truth and you will predict for the future. So this is the task of your model. Okay. So we can start, right? Can you start?
Please, yeah, sure. Please start.
Okay. So here we left, right? This is our cost function. How the cost function is computed here? Basically, this is the error. So this is the predicted value by your model. So you are giving X as input. Your model is predicting that the house price is 180K. But for this example, you have a value like you have already observed that the value is 200. So this is the difference between predicted and ground truth, or predicted minus observed. Ground truth or observed, that you can use any term. So we normally use square of the error. So this is just for simplicity of the derivation we use. And also you can see here another term, half. So you will see like why you use half, because it will make our derivation easier. So this is our cost function. So every learning algorithm has a cost function. So what is our goal? Our goal is to find a cost function that find a cost function j theta, which is minimum. Basically, the function h theta that gives you the smallest error. So here, your objective is to find theta, basically find theta. Here only unknown value is theta. All other things are known. So you have a hypothesis, you know this. Your y is known, your x is known, only theta is unknown. So you have to steer the theta and find the theta that will give you the minimum value for this function. That's why we call this cost function. Okay. So one visual example, I think this is very important slide. So how does like cost function look like? So here we are assuming that this is our hypothesis space. Hypothesis space means just x is parallel line. So this is one hypothesis, this is one hypothesis. And for each hypothesis, you have a value of j theta, right? What is j theta here? Sum of the squared error. So using that formula, you can just have a hypothesis and a dot here. Another hypothesis, dot here. Another hypothesis, dot here. This is basically sum of squared error for all examples. Because for this hypothesis, error is much higher than this hypothesis, right? That's why this is the error, j theta, value of the j theta. Okay. So this is your function. This is called j theta. And you know, like from our elementary school algebra, how to find the minimum, of a function. What is the minimum of this function? Which theta gives you minimum? This one, right? This is the minimum of this function, and we need to find this theta, this value of the theta. So how to find this theta that gives you minimum j theta? So this is our question. So here comes one optimization algorithm, which we call gradient descent. Gradient descent is widely used not only in linear regression, in all machine learning algorithms, even in deep learning algorithms. What does it say? In gradient descent, you start with a random theta. For example, this is our first theta. And here you will find the slope, the gradient. And then this is theta 0. Then you will update the theta 0 or theta, just a normal theta. You will update the theta in the direction of your gradient. So here, the direction of this one. So you will just update your theta like here. Again, you do a gradient here. Again, you will update your theta. Again, you will do gradient here. You will update it, and then you will find a theta that minimizes this function. So this is the same thing, gradient. Gradient, you have a theta. What is J? I'm coming it later. And you are updating this theta with the derivative of your function. This is the derivative, right? So if this is a function, if this is a point, at this point, this is the derivative. So you are finding a derivative of J theta and multiplied it with alpha. Alpha is called learning rate. So how fast you want to move down or how fast you want to move towards the solution. This is alpha. And what is J here? J is the input dimension. I think you can remember the input dimension. We had how many dimensions? X1, X2, Xn. For a particular X, we had Xn dimension of input features. So for each dimension, theta will be of similar dimension because in our function, what is theta? H theta x, it was theta 0, x0 plus theta 1, x1, dot, 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 theta n, xn. So basically you need, theta is one thing, but its dimension is n plus 1 here, theta 0, theta 1, theta n, right? This is the theta. So for each theta, each dimension, we have to find the derivative of the function with respect to that dimension multiplied by learning rate. And we are just deducting this from our original estimate. This is how we are updating theta. Okay. So this is another example, a pictorial example. This is two-dimensional feature space. So if we start from here, where is the minimum? Minimum may be here or minimum may be here. So what if it starts from here, it will just come like this. And each time it will find the derivative of this function and go downwards, go downwards, go downwards, go downwards, go downwards, and this is the minimum. Okay. This is the same example. This is like contour representation. Contour representation, if this is a two-dimensional curve, we can draw the contour of this. And this is just, you can see that from here we can start and then move towards minimum. So this is how gradient descent works. So then what is the algorithm of gradient descent? How can you find? First, you need to find the derivative of J theta. We have seen that for one particular example, single training data point, this is the error, right? So if you have X as input, H theta will be your predicted output and Y is your observed or original ground truth output. Then this is the error that we are using. So we need to find the derivative of this function. This is simple calculus. So finding the derivative of this in terms of theta j, so we know the square terms, it will come first here, then half, and this one multiplied by, again with respect to theta j, we can find the derivative here. And here 2, you can just cut it, h theta minus xy. And from this term, what will remain intact? Only xj, only xj. So there are, this is from x1, x2, xj, xn. Since you are like finding derivative with respect to theta j, only this term will remain and other terms will be crossed out. So that's why the derivative is so simple here. Okay. So you can see this is proportional to the error. Error is h theta x minus y, just multiply by the feature. So this is the derivative. And now what we need to do for a single training example, we need to update this for theta j equal to theta j plus y minus h theta x. This is the error and this is the term for a single training example. Here superscript is example. I1, 2, you have m examples. This is the superscript. And j is features. 1, 2, n. For each examples, you have n features. That's why this term. So here, this is the update rule. This rule also called least mean square update rule or Woodruff update rule. Okay. So this is, so now the algorithm is, so there are two gradient descent. We can update, right? But we need to update for all the examples. Here in the previous slide, we have seen we are just updating it for single example. But for each iteration, what we have seen here, for each hypothesis, we are computing the error for all the examples. That's why here we have to find errors for all the examples. That's why summation of I1 to m. For all examples, what is the error? For example 1, this is the error. For example 2, what is the error? So this is all for all examples. And multiplied by learning error and here theta j. I think you missed one point. There is no question because I started with different formula, right? Theta j minus. Here, what we are using? Here using plus. Basically, this is the same thing. Previously, we were using h theta xi minus yi, right? Now we are using just negation of this yi minus h theta xi. That's why this negative becomes positive. Okay. And this will just run for every j. Every j means like if you have n dimension, then you have to run this for every j. And this will continue. This will not stop. So this may be, it will run for like 100 iteration or 1000 iteration until the program finds the minimum. Okay. So there is another. So if you have very large data set, sometimes it's problematic find the like gradient, like find the error for all examples and then make a step. Rather than this, you have another option, which is called incremental gradient. In the incremental gradient, you can update your formula for each example. Look at the difference. For I1 to m, for each example, we are updating theta. And in the previous example, we are updating theta j for the errors of all the examples. Okay. So this is the main difference. So what is the benefit? Incremental gradient descent is faster, but it may give suboptimal results. So it can just roaming around and then give some results. But it's close to the optimal. But the batch, it is costly, it takes time, but it gives a good result. These are the two main difference, right? I think just one point. So I think from the elementary calculus, you know, like how to find the minimum of theta, right? For every function, how to find the minimum theta that will give, how to find the value of the theta, which will give you the minimum of j theta. Basically, in the calculus, we found that if we just find the derivative and make it 0, then it will give a closed solution, right? The theta will give you the solution. But here, there also exists some solution in the closed form. So if you find the derivative of the function and equals 0, then the solution will look like this. But we generally don't do this because this is very costly operation. Okay. Okay. So next, I think I am quite behind the schedule. So maybe I will skip these things. This is called locally weighted regression. This is another form of regression. I'm just telling you the problem. So basically, this is one concept. That's why I want to discuss this. So you can have different kind of hypotheses, right? For the same set of training examples. Here, you can have a straight line. Here, you can have 2-order polynomial. Here, you can have 5-order polynomial, right? For this theta, it seems a little bit underfit. It does not fit really well to the training set. But here, it seems it's really fit well to the training set. The error will be much less. But here, it seems it's overfit, but it just go through every training example. But if a new training example comes here, you will find large error. This is called overfitting. To avoid this error, sometimes we use locally weighted linear regression. Okay, just to give you an idea. So I'm just keeping these details because I don't have much time locally. Then I'll move to the classification. So maybe up to now, if you have any question, you can ask me in chat, maybe in the linear regression, then I can move into the next one, classification one.
Please feel free to ask if you have any question. Okay, so they are writing to you directly. That is why I'm not able to see.
Okay. So first question was,
Yeah.
it is just a curve fitting problem. Linear regression is a curve fitting. It's not basically curve fitting because it may overfit. My last example was it can overfit if you just do the curve fitting. But yes, basically, I want to find a representative line, not curve, representative line, because if you do the curve fitting, then it will be very complex. Just find a representative line so that I can give you answer for an unseen problem. So this is the main difference. Yes, you are right. Like another one, Manoranjan, yeah, dy by dx equal to 0. Yeah, you are right. And you can find a closed form solution of that. Yeah. Anyone? I think I'm assuming that linear regression is now okay. I think this is the very basic problem, but it is widely used. Still, it is widely used for many problems. Yes, the minimum value is the optimum solution. Yeah, right. Any other question? Yes. Okay, we are moving. Okay. I think that next I'll go to the classification. So what is the classification? So I think I have already discussed this. That when the target variable takes only a finite number of discrete values, then it is called classification, right? Like if you want to classify your email, spam or non-spam, if you want to classify some handwritten digit, so it can be only 0 to 9. If you want to identify whether the tumor is cancerous or not, this is binary classification problem. So there are lots of classification problems. And if you want to identify whether the image is from image is dog or a cat, so these are all the classification problems. Okay, so can we solve classification problem using regression? So let's have a look. So here in the classification, you have only two data, no continuous. Y can only, so I am assuming binary classification first, binary classification, okay. Y can be only 0 or 1 if it is binary. Maybe you can, in terms of house, you can say whether price is high or low. Okay, high is 1, low is 0. Then the level data will be look like this. These data will have level 0 and these data will have level 1. So now if we just try to fit a line like this, what is the problem? So you can have an unknown example, an unknown like house who has living area like this. Then using this line, you can predict this something like 2, but we have only 2 levels. So this is, it doesn't make sense basically. So we cannot use regression for the classification problem. But what should we do? So there comes logistic regression. So in logistic regression, this is little bit of different than linear regression, but I think conceptually there are lots of similarities between these two. As you can see here, for h theta x, in our previous example, in linear regression, h theta x was only theta tx. Here, h theta tx equal to a different function that is bounded between 0 to 1. This function is bounded between 0 to 1. You can see here, this is the function. Okay, so basically here z equal to, you can say, theta tx, and then you can have a sigmoid function which maps your z value from 0 to 1. Okay, you are getting same value. Like in linear regression, you are getting value theta tx. It can be 100, it can be 200, but you are just squeezed this value from 0 to 1. This is the like goal of the sigmoid function. So this is our hypothesis. For example, here, same, this is h theta x, this is a sigmoid function. This is again the linear combination of your input features, theta tx, but we are using it differently so that it only gives you value from 0 to 1. So if z is like minus infinity, then it is close to 0. If it is plus infinity, it is close to 1. It just touches there, right? There, it will be like this. It will be like this. Never, it will be never greater than 1 or less than 0. This is the properties of the sigmoid function. We will use this. So there are many other similar functions, like you will see in deep learning and any other machine learning, they are different. But here in logistic regression, we will use logistic function. So here, for this is x, and we have label, okay? And this is another sigmoid function, theta tx, or you can say z. Then you can plot it here. Plot it here like this. Okay? If you plot this, x and theta, then it will look like this. Okay? It will look like this. Using this function, we'll do logistic regression. So now we'll go to little bit like details in terms of mathematical formulation. So first, I think I should just discuss these things. So it is bounded by 0 and 1. So I have already discussed this thing. This is bounded by 0 and 1. This is 1 and this is 0. Okay, this is sigmoid function. And another property is, if you take the derivative of this function, it comes to a very like simple formula, zz 1 minus zz. So if I go to the details of this derivation, you can, I think, use simple like high school math. So if you just find derivative, it will be like this. Okay, so we'll use this one later. Okay. Now, how can we formulate the logistic regression? So basically, you have two classes, right? One is positive, one is negative, class 1 and class 0. So I want to find a function. Okay, this is the positive class function. Basically, probability of y equal to 1. So if you are given x, what will be the probability of x belongs to class 1? This is what h theta x. And the reverse, given x, what is the probability of this x belongs to class 0? This is just the opposite, as this is the probability. H theta x is this. If x is not here, like for example, if x is class 1 with probability 0.8, what will be the probability of x being class 2, class 0? It will be 0.2. You can look this function again. If this is h theta x, okay? If this is h theta x, so this is the probability of x belongs to class 1. So these are all the probabilities. You can say this is 0, this is 0.5, this is 0.1. So if your input is here, what is the probability of it belongs to class 1, y equal to 1? It will be 0.6. If x is here, the probability is 0.95. If x is here, what is the probability of x belongs to y equal to 1? It will be 0.2. Basically, then probability of being in class 0 will be higher. If this is h theta x equal to 0.2, 1 minus h theta x will be 0.8. Then you can say this is belongs to class 0. Okay. So for the binary classification, you can have these two formulation. What is the function? What is the hypothesis of this? Hypothesis is this one. And 1 minus h theta x is probability of y equal to 0 given x and parameter theta. If you combine these two, you will get basically same formula. You are just combining these two equations. You put here, you put y equal to 1. What it becomes? Y equal to 1. Here y equal to 1. This whole term becomes 1. Power to the 0, 1. So it only remains this. If you put y equal to 0, this term becomes 1 and only remaining terms is this. So you can actually write this two equation using this one equation. Okay. So this is our formulation. Why you use this formulation? We need to have some kind of cost function to optimize. So this is we call L theta, likelihood calculation. Likelihood means we have to find a theta for which this probability becomes maximum. What is this probability? Just the product of all the probabilities. For example, you have level data, right? You have level data. For example, 1, you have +1. For example, 2, you have +1. For example, 3, you have 0. For example, 4, you have 0. So these are x, these are y. Okay, these are y. And you have to find the theta for which you will find the maximum probability for this training set. So that's why this is called likelihood calculation, likelihood of theta. Find the theta that will give you the maximum value. And this is the same. If you replace this one, as we see here, you can replace this equation with the detailed term. Normally, for the simplicity of the calculation, we use log likelihood. I think every one of you know from like elementary calculus. If this is the likelihood, you can use log likelihood. Take a log, then the product term becomes summation. Then it is easier to find maximum or minimum of this function. Okay, so this is the theta, L theta. And now, again, so we want to, so apart from like in linear regression, we have to find the minimum, find a theta that minimizes the function. Here, this is the likelihood. So you have to find theta that maximizes this function. Okay, you have to find a theta that maximizes this function. That's why this is called gradient ascent. Okay, so you can again find the derivative. I'll not go to the details, but you can just check later from these lecture slides or some books. So if you take the derivatives, you can find here, just you can take the derivative of these and go to this, and then this, and then this is very simple thing. Because we have another equation we have seen, z prime z prime z equal to zz 1 minus gz. Here z equal to theta tx. If you replace this, if you use this term will be very simplified term to this. Okay. So can you find the similarity between logistic regression and linear regression? We have started with completely two different formulation, but it turns out that this derivative becomes almost same, not almost same. So we have the same derivatives there in linear regression. Y minus h theta x multiplied by x. Here, y minus h theta x multiplied by x, right? Same function. So then you can use this one. Similarly, our gradient descent or gradient ascent algorithm, theta j plus learning rate multiplied by this is del theta j L theta, here L theta. Okay, this one. This term here is this one. Okay, so this is logistic regression. So you are just using different formulation, different function to convert linear regression to logistic regression. Okay. Any question? I think I have covered a little bit of mathematical details, so I think I should take question now. Any question? Yes, multi-class classification is possible. You can just check the book. Same thing. So this is not, I have just shown the binary, and you can extend it to multi-class classification problem. Any other question? So I think the programming language, yes. Programming language, I think next lab class will cover that one. And you will, now it's easy. You can just ask ChatGPT to generate formulation for this logistic regression in any language. So it makes, I have to cover, so I'll not cover anything now using any programming language. I think the next session will cover using Python. Okay, I'll just cover now SVM, support vector machine.
So next
Any
session we
other
will have
question?
this next session we will have this lab actually,
Yeah.
where
Yeah.
you will use SVM in classification and
Yeah.
regression. So you will be able to do the coding.
And regression too. Yeah.
Yeah. And this is, I think, only 2-3 lines of code, because you don't need to find the main, I think the key point here is that you don't need to find this derivative again and again, because after the derivative, it comes to a very simple equation. You can just even implement this simple equation. Okay, I think there is no other question. Okay, great. Okay, so there are many applications. I think I'll so this logistic regression is very simple, run quickly, and gives real probability. As I can see, though I'm giving output 0 or 1, but basically it gives you a probability. So you can use this probability to determine something like very sophisticated things. Okay, so the main disadvantage is needs huge amount of data to reach a stable state, and also does not work for more than one decision if it is very complex. So I am just covering very simple binary classification, which is clear boundary. Okay, so the application wise, you can do you can apply to many things. So bankers can use it to predict the chances that loan application will be default on the loan. This is binary. Marketers can use whether a customer will respond to a particular ad. So these are all binary classification. And for email classification, you can use it actually K, not only binary, K classification. And here is the quiz, like what is the cost function? Basically, I have covered. For linear regression, J theta, this is the cost function. And for logistic regression, cost function is this, like this one, right? L theta. Okay, this is the cost function. And the main difference, one is gradient descent, because I want to minimize, and another is gradient ascent, because I want to maximize. I want to find the maximum. Okay. So next, I'll go to support vector machine. But before that, I think I need to discuss little bit of perceptron, because there is a motivation of support vector machine. Okay, I think you know already the perceptron. Perceptron is basically a classification algorithm that finds a linear separator. For example, if these are one class, if this is another class, I want to find a line that separates two sets of examples. Okay, this is called perceptron, very basic. And again, this is basically linear combination of all features. So in the perceptron, what we do, I will use now W just to avoid the confusion. In linear regression and logistic regression, I use theta. This is the parameter. Here also W is parameter. You can use also W. But for the support vector machine, I will use W. This is same as theta. So WTX plus B, because you are finding a line. Okay. This is the linear combination of input features. If you have lots of input, so you are basically using linear combination of this feature. And if this linear combination, basically you can write this as same thing, greater than 0, then you can say this is positive, class 1. If this is less than 0, you can say this is class 0, negative. So this is called perceptron. So you have to find a line. So what is the difference between logistic regression and perceptron? Here you can see logistic regression gives you a probability This is a probabilistic line, 0.0, 0.1, 0.2. Perceptron give you just clear-cut boundary. If theta tx or wtx is greater than 0, the class level is 1. If wtx is less than 0, the class level is 0. Okay, but this is, you have to find w. This is called w. This is based on w. This is a separating line. This is not a w, sorry. So this is a separating line. This is wtx plus b line. So this is simple perceptron. So you will use perceptron in many algorithms in deep learning and many other things. But here the main purpose is to motivate you for support vector machine. Okay. So this is one linear separator. Okay, linear separator, as I said you, there are two classes. One is red, you can say it's positive. Another is blue, you can say it negative. Okay. And now this line represent this equation. On this line, wtx plus b equal to 0. In this line, it is less than 0. And in this side, it is greater than 0. Okay. So this is finding, binary classification, finding a separating line that separates two classes. Can anyone answer, like, what is W here? Where is W? So this is a line, but where is W? Anything in the chat box? No. Okay, I'll come to that point. Where is W? This is important. Okay. So it is easy, right? There can be many separating lines. So you can see here, we have two sets of examples, but many lines can separate it. This line also can separate, this line can also separate, this line can separate this line. But which one is optimal? Which one is the best line? So that where the support vector machine comes. It is not only sufficient to find a separating line, because separating line, you are finding the separating line, this one. But when the real world example comes, maybe one red dot comes here. But based on this line, you are classifying this as a negative example. This is not true, because based on this, it should be positive example because it's very close to red. Again here, if you choose this line and a green, a blue dot is here, then this is wrongly classifying this example. So finding the best line, best separating line is important. So that's why we'll study the support vector machine. Support vector machine is widely used. Like before deep learning, I think these support vector machine have been used in many applications. But nowadays, because we have lots of data, we are moving towards deep learning and other things. But still, in terms of theoreticality, in terms of conceptuality, support vector machine has many things that you can study. Okay. So what is the best line? For example, if you look at this example, so there are many separating lines, but we are saying that this is the best line. Because we want to find a line like that has the maximum distance from its closest point, which we call support vectors. So basically, we have to find a line so that the separation from positive and negative example are the most. So if we draw a line here, What is the separation? What is the distance from negative example? This is little. Again, if we draw a line here, what is the distance from the positive? Little. But if we draw a line here, this is the maximum distance from positive and negative example. So in the support vector, we'll find this line. And how to find this? I'm coming to the details, mathematical things. I think you first need to know a little bit of vector to understand these things. So basically, so I think I draw just a plane, not a line. So in a two-dimensional, you can draw a line, or in higher dimension, you can draw a separating plane. This is a separating plane. It's easier to explain. That's why I draw a separating plane. And on this plane, this is a separating plane. This line in higher dimension, it can be seen as a plane. So here I'm assuming 2 points, x prime, x double prime, 2 points. As this is on a plane, what is the equation of this line? W2x plus b equal to 0. We have seen it. And this is the same. On the plane, everything is 0. So you can write W2t x prime plus b equal to 0. You can write WT x double prime equal to 0. Okay. And if you just combine these two, you can write this. Add these two equations, you can write this. BB cross out, and then you will find this equation. The main purpose of this equation is to show where is W. So W is always perpendicular to the partition, like this, perpendicular to this plane, this W. You can see, because when two perpendicular line, we take a dot product, it becomes 0. So this is a line, and this is a W transpose T, and this line. As this is 0, you should think, like it is verified that it is proven that W is perpendicular to this plane. Okay, because any two vector from linear algebra, if two vectors, if you take the dot product, if it is 0, if it is perpendicular, it will come as 0. Dot product is 0. So that's why W is 0. So now I'm computing a distance. Now assume xn. So for example, this is the closest point. Let's assume this is the closest point of this plane. Okay. Now I need to find this distance. And this is, we can assume another point on the plane, on the separating plane. Okay. So now you just draw this line. This is a vector. And you draw the projection on W, because W is perpendicular to the plane. You draw the projection, not on W, the unit vector. W can be many things, because a vector, if you don't define it as unit vector, this is W, this is W, this is W. It can be like many vectors, same W, but different scale. So this is, you can say the W, we are defining a unit vector. Unit vector, just you are normalizing the vector with its norm. This is called unit vector. So we are doing the projection of this line on the unit vector. Then this is the distance. This is the distance, xn to the plane. So now let's, I think here's some problem in the presentation. Some equations are broken. Okay, I'll try to make it clear. So what is the distance? Distance is the, like this is a line, and if we project this onto the unit vector of W, then this is called the distance. That's why this W hat transpose multiplied by this vector x and x. Okay, this vector. This is the distance. And what is this? So I'm writing it again. transpose. Okay, this is the distance. If you do the projection. Now this distance, if you just elaborate this, okay, you can write this WT, this norm is here, normal W transpose xn minus W transpose x. Now you can introduce B here because I'm assuming B is not here. So again, you can write W transpose xn plus B minus W transpose x minus B. Okay, this and this plus B minus B you can cross out, but let it be there. Now, what is this value? Can you say? W transpose x plus B. Anyone? This is on the plane. If it is on the plane, this should be 0. Because this is the equation of the plane. WTX plus B equal to 0. Any point on the plane, it will give 0. So this is 0. So just cross out. Then what is left? The left part is xn plus B. Okay. Now you can make it 1. You can assume, like we are assuming WTXN plus B equal to 1. We can make it by scaling W. So if we change the parameter W and B, we can make this figure to 1. Okay, this one. So now we are assuming, let's assume this is 1. So we can change parameter W and B such that it becomes 1. Because your xn is fixed, you can change other parameter to make it 1. So then this is the distance 1 over W. What is this distance? This is this distance. This is our nearest point, and this is your separating plane. The distance is this one. Okay. Then what should be this one? It should be 2. Then what is the problem in support vector machine? So we have to maximize this, right? We have to maximize this. So this is like overall idea. Like we have to maximize this. We have to find a plane. We have to find a separating line that maximizes this. Okay? I'm going to a little bit mathematical details here. So this is the slides that discuss these things. Again, a little bit of like simplifying things. So when you have a line, we can assume, so this is separating line, this is nearest point, this is another nearest point in two sides. So for each training example, we can see these are positive. Each training example, we can say this. Okay, WTXP greater than equal to 1 if yi equal to 1. And for each negative example, we can say this one. Here term 1. Remember, this is not 0, this is 1. We can assume this because we can because we have made like this. WTXN plus B equal to 1. Nearest point, distance to the nearest point, because this equation we have made that the W2XN plus B, that the line that goes through XN equal to 1, because we have assumed that, right? We have assumed that. So all the points there greater than 1. All the points here less than equal to -1. And on this line, all are equal to 1. That's our assumption. And if we just combine these two, this is just for a constant. I think you can understand, like if you just go to these slides, you'll understand better. But just to formally define SBM. So if you just combine these two equations, like yi is negative for this one, yi is positive for this one. If we multiplied this left side with yi, you can basically combine these two formula into one. Just multiply yi left side, right side, it will be same thing. Yi left side, right side, it will be same thing. So this is our constant. That's the main thing. This is our constant while we want to maximize this. Okay. So this is the slide. So finally, support vector machine, we have to find W and B such that the width of the margin is maximized, and we have seen that the width is 2 by W. And for all xi, where this constant must satisfy. Okay. This is a constant satisfaction problem and quadratic optimization problem. And we can just little bit of like, if we do the quadratic programming, that will work for minimization problem. That's why if maximizing this is equal to minimizing this, because if you want to maximize this, rather than you can just minimize this, same thing. So you can minimize this under the same constant. And now, and the same constant. And now how to solve this one? I think this is little bit mathematical. I'm not sure whether you'll be able to understand, but still I'm going through these things, okay? So this is basically an optimization problem, and you can solve this quadratic function. Quadratic function means this is W square, right? WT transpose W equal to W square. If you know the linear algebra, transpose matrix multiplication with itself is square. This is the same thing. W transpose W equal to W square. Okay. So under this constant, so this is quadratic function and some linear constant. And you can solve this problem using Lagrange formulation. And how this terminology comes, so I need to basically go through some equations. I think I can quickly go through some equations if just little bit permission. Professor Aparajita, so should I go to the details? I'm not sure, like the participants. So should I go to the equation details?
The participants have, I believe this is a heterogeneous group. So some of them may be aware and many of them may not be aware too. So can the participants please write yes or no, so that because
I'll just then go very high level, because this is a little bit of mathematical things here. Otherwise I'll go just like in overview kind of thing. It's also fine.
Participants, if you would like.
So do you like to hear more details of this formulation?
Please write yes or no. Yeah.
Yes, one. Other participants?
I think you can give some details, because these details are, I mean, they find problems in understanding these details. So if you can give some.
So I think I'll go. Okay, fine. Okay, thank you. I'll go some. Yeah. Okay, so basically, so then I should go to a slide. Okay, here. I think I should. So what we have done, so we need to minimize basically these things. And we have constraint. What was our constraint? Yi wt xi plus b. This is our constraint. So here, what are the parameters? One parameter is w, definitely. Another is b, if I just write a function b. And another is if I represent this using Lagrange, these are called Lagrange coefficients, this. Then we can write this formulation like this. And these are coefficient yi okay. So we can write like this. So this is our function. This is our optimization function. Okay. And here, if we minimize this, so we need to minimize this. So we need to find derivatives of this function. So first, if it is matrix form, we can find with respect to w. And another derivative we can find with respect to b, two equations. We have these two parameters, and other is just coefficient we need to solve. So for this equation, if we take the derivative of this, we'll find something like, you can work out at home, n alpha yi xi equal to 0. Because again, the derivative, when our job is to minimize something, so we have to take the derivatives equal to 0. This is 1. And for e, we'll find okay, this one. So these are the two equations. So this is the main equation, and then you can find this. And if you substitute these things, like here one, we got w equal to what? W equal to this one, equal to 1 n alpha y x. Okay. So, and this equal to 0. So if we substitute in this original equation, okay, in this original equation, so what we can do, we can just expand this. Okay, we can just expand this and find just one step ahead with what we'll get. If we substitute this to there, we will get I equal to 1 to n alpha minus half I equal to 1 to n equal to 1 to n yi yj alpha I alpha j xj. Okay, so we'll get this term. Okay, and this is basically alpha, because we have just removed all the items, and this is a function of alpha. Okay, and after substituting this, we get this one. And here we are maximizing. So for with respect to here, alpha greater than equal to 0, and we have another equation, this one, alpha I yi I equal to 1 to n equal to 0. Okay, these things. And when we put this, then this is like normal quadratic programming. You can do any quadratic programming. If you want to solve this, you will get alpha 1, alpha 2, these things. Okay. And from this alpha 1, alpha 2, what is W1 now? if you get, like if you solve this using quadratic programming equation as a minimization problem, any like package, Python or other thing, so quadratic programming, and then you will get this alpha 1 to alpha n. And from this alpha, you can get W. How? Here is the W, right? W equal to alpha yi xi. Yi is given, xi is given, and now we found alpha, then you can find W. So this is one parameter. Okay. And then you can also compute B. Another parameter is B. How can you find? This is WT xn plus B equal to 1. We know. For these support vectors. Then if you put W, then you can find B. So from this equation, you can find alpha first, then W, then B. So after finding this, what is your job? Your job is to predict, right? So now you have basically separating line. So this is W, this is B, and now if you have some unknown value, you can classify using this. And this W and B will give you the separating line that maximizes the width from positive and negative sample. Okay, this is called support vector machine. Why we are calling it support vectors? What are the support vectors here? Support are these vectors, these samples that are on the boundary. These are called support. So when you compute these things, this alpha only for support vectors, these examples, alpha will be positive. For other example, alpha will be not positive. So you have only few parameters for computing the support. So when you compute W, once you get alpha, you will find lot of alpha 0. Only few alpha which is positive. These are the support. And that's why we call it support vectors, because they are supporting this boundary. They are supporting this margin. Okay. Okay, I think we are there. So in summary, so I think we have seen quite a lot of like things today. I'm not expecting that you can understand these things if you don't have any background previously. Because normally what we cover, normally in class we cover linear regression in one class, logistic regression in one class with little bit of mathematical details. Here I omitted many things, and support vector machine in 1 or 2 class. Okay, but I think in summary, I think you got a good idea, like what is the problem of regression, what is the classification problem, and how to solve using normal logistic regression, binary classification. And then we move to a different types of machine learning, which is called support vector by SVM, that not only find a partitioning line boundary, it also finds line that maximizes the separating margin, which is called support vectors. These are the vectors, support vectors, that are supporting this boundary. Okay, I think now I'll take question from you.
I would like to add here, please, participants, please don't write your questions on Asia Connect ID, because that ID is actually handled by the Asia Connect staff. So if you have any questions, so either write it on everyone, or you can write it to Professor Ali. And I will say that if you will write your questions on everyone, it will be easy for, because when Professor Ali will answer those questions, it will be easy for us to understand. So don't write, I mean, your problems on Asia Connect ID, right? So please write it here, yeah. Okay. No, but, oh. Okay, in that case, either write to Professor Ali directly, write to the expert, or you can write it to us, like either myself or basically on the coordinator. Because from the Asia Connect, they need to tell actually. Okay, let me check for this option. Yeah, because I'm getting this option. Just a minute. Yeah.
I think maybe everyone understood it correctly or no one
So,
understood anything at all.
if you are having any question, either you can rewrite it on the to share it with Professor Ali, or you can share it with me.
Write it to me. So many participants already did it, and I got I got quite few questions earlier. So you can write if you have any. Otherwise, maybe thank you everyone.
So any question, please, you have 2 to 3 minutes. Please, Professor
I
Ali is there.
support
Please write
vector
it.
machine, there are two resources that I have followed. So one is Professor Abu Mustafa of Caltech, and another is N. from Stanford. Both are good for SBM. And I think this is very old technique. So you will find lots of book and very good description.
Yeah, it is available. I think they most of us find problem in understanding that optimization part.
Yeah, I think this is very hard. This is hard. But I think good thing is that in optimization you don't need to do this yourself.
We have a question.
Most of the packages are able.
Yeah, Professor Ali, we have a question. I think one of the question he has already although answered, but still, what is the purpose of support vector? They maximize the distance, but the plane that is WX is already separating the observations.
Yeah.
So their question.
Many separating, but
Anisha is asking this question.
Yeah. There are many separating planes, but which one maximizes is our objective. And the points that are acting as a support vector in our solution, which is called support vectors, right?
So this was the question I have ordered it.
Okay. Yeah. This is not a purpose. Like purpose is to maximize the width. Then we name these vectors, which are the closest point. These are the support vectors. And we see that calculating W only we need this support. We don't need other X, other examples. So this is one application. So you don't need many other examples. If you have hundreds of examples, only 5 support vectors, then you can quickly calculate your W using these 5 support vectors.
So any other question?
Okay, Ayush, thank you. So I think
in fact
some concepts have been cleared. Yeah.
You have explained things in such a clear manner, so that the participants are, I hope, they were finding it easy. That is why not so many questions. And
thanks. That's good for me too.
So if there are no questions, then we would like to thank Professor Ali for this wonderful talk on the machine learning. This basically regression and SVM classification. So we thank you, sir, for explaining all the concept in such a easy manner. And I hope we are sure that participants have been benefited from this, and we will be in taking your help in future also in all lectures. And he is also one of the member of this project. So he's always a part of a team. So thank you so much, Professor.
Thank you, everyone. Okay, bye.
Yeah, thank you.
Bye, Professor.
Okay. So Neha will share the link of